Energy Institute. We got a similar one called Birmingham Energy Institute, and it's also quite interdisciplinary. We have experts doing engineering, power system, computer science, social science, economics. So it's quite diverse. Yeah. So this is the topic I will present today. It's the main method I use is the digitalisation. So it's mainly for data-driven solution, machine learning, and AI. And the way we do the research is the place-based approach. That means we tailor our data-driven solution to the resources, condition, and the constraints in each local area all over the city and globally. And also we do the whole system integration. For that one, we integrate multi-vector energy system, including the electricity, heating, cooling, and also transport, and across different sectors, like the industry, the built environment, and also like healthcare sectors. And the final purpose, we want to move the energy system to clean net zero transition. Yeah. And this slide shows some pictures of our campus and our city. So our University of Birmingham is based at Birmingham. It's the second largest city of the England. I think in US also, we have Birmingham as well. Yeah. And we call ourselves the Energy Valley of the Europe because that's the origin point for the Industrial Revolution. Yeah. And on top, that's our campus. You can see from the picture, it's made of red bricks. So we are the origin of the red brick universities. Some similar universities like University of Sheffield and Glasgow, this all red brick university that track back to the Industrial Revolution period. And also, we are one of the Russell Group University. I'm not sure if it's equally strong like the Ivy League, but that's kind of prestigious top university in UK. And this is a bit information about myself. And thanks for Rahman, the kind of introduction. So I joined the University of Birmingham 3 years ago as assistant professor in engineering. And before that, I did my postdoc in Oxford University and Cardiff University. So Cardiff is the capital of Wales, and Oxford is quite close to Birmingham. So Birmingham is located in the center of England, and I think 1 hour by driving to the Oxford. And I got my PhD from Durham University, that's in northeast of England. Yeah, and in terms of the research focus, I mainly look at 3 areas. First is, as I introduced at the beginning, about the whole system, place-based multi-energy system modeling and optimization. And the second part is more about methodology. So it's about visualization, data analytics to help with the planning and operation of energy systems. And the third aspect is more about the market side, the energy system economics. So I look at the trading auction mechanism and how we can better support localized energy trading, community energy sharing. Yeah, and also at the bottom left corner, recently we need to publish 2 books about the digitalization of energy system and the potential application of AI and distributed ledger technology to assist the energy trading, energy system planning, and operational management. Yeah, and this is a number of research projects we are recently leading on, and we put 6 buckets. It's for 6 different focus. For example, the hydrogen integration in energy system, the clean net zero energy system transition, the climate resilience, and also multi-vector cross-sector integration. Also, we look at the social science aspect with data-driven solution. So we analyze the socioeconomic and the demographic data to identify the vulnerable group over the course of net zero transition. So the vulnerable means like economic hardship, the fuel poverty. So that means if we want to move the entire energy system to net zero, we don't want to lag any group behind. And on the right-hand side, these are some of our close collaborators in the UK. So for example, we have the Catapult, that's kind of government department, government research institute, leading the nationwide strategic priority areas, like we have the energy system catapult, which focus on the energy system transition. Also, the connected places catapult, that's more about the transport, the urban planning, and the built environment. And also, we work with the power system operator, the transmission and the distribution network operator. Like in UK, we call it the NESO, the National Energy System Operator. That's for the transmission network in England mainly. And also for DNO, distribution network operator, we work with SSEN, Scottish Power, and also National Grid. They have the particular department for the distribution network, the National Grid electricity distribution that cover Birmingham area. And this is our lab facilities and equipment. I think for this architecture, the smart grid lab, that's most common for all the electrical power group, all the university with electrical power system facilities. So basically, we do the stable physics modeling for all the components of the power system. In particular, we look at the medium to low voltage distribution network. So we have the 11 kilowatt transformers and also three-phase power source. For renewables, we have the solar and wind emulator. And also for the converter or inverter, we have AC to DC or DC to DC programmable inverters. Also, in our lab, we have the V2G facilities and the EV charging facilities, as well as the hydrogen fuel cell to put multi-vectors into the electricity power system. And also from the communication side, we have the protection and the automation layer. That's mainly to measure the communication across different components of the power system. Also, we can do the hardware in the loop test, the digital simulation, like the RTDS, the real-time digital simulator, and also the OPPO RT, which can model the real-world operational scenarios for the power system. This is my own group, as Rahman introduced. It's called SEAL, Climate and Energy Informatics Lab, and also I put the logo on the top right corner. Currently, we have 10 PhD students covering different areas of energy system, all filling within my research scope. And we are also hosting visitors. Last year, it was the 125-year anniversary for University of Birmingham, and we opened the fellowship globally, in particular for the global south countries, and to work together on the clean energy transition. This is the outline for today's topic I will cover. So at the beginning, I will introduce a bit of the modeling, how we integrate the energy market modeling with the physical operation and the planning of electrical power system. The second part, I will introduce some technical research project we are recently doing, how we integrate different vectors, different sectors together for the energy system to maximize the synergy and also maximize the flexibility. And the third part is move from generation side, more about demand side, the low voltage distribution network, how we use the data-driven solution, machine learning, AI solution to assess the planning and operation of local energy system. And also from market and the economic side, how we can help with community energy sharing, how we design the pricing and the negotiation mechanism. At the beginning, a bit background for the electricity market evolution in JB, because I think the JB electricity markets, they go to the decentralization and liberalization. It's the first across Europe or probably globally. Yeah, so that take back to 1990. That's the first year. Before that, we only have one national-owned company. It's called CEGB, the General Electricity Generating Board. And it's really vertically integrated for all the functions from the generation, transmission, distribution, and retail function. So since 1990, we have vertically unbundling. That means we separate these individual functions to individual companies. They are not interrelated. They have the independent audit and management system. So for the generation side, at the beginning, we have two companies. One is National Power, another is the Power Gen. So some of them look at the coal-based generation, that time the coal is still the dominant power plant in the GB, and some of them look at the nuclear generation. And for the transmission network, it's evolved as a national grid company. This is, I think, the former shape of the current, I just mentioned, the NESO, the National Energy System Operator. And for the distribution and the retail function, they evolve as 12 regional electricity companies. And all these 12 companies, they are privatized, and they sell the stock to the individual owners so they can manage their own cost and benefit. And also, at this point, we create the first wholesale market. At the beginning, the shape is electricity pool. That means all the buyer and the sellers, they submit the bid and offer in the centralized market clearing mechanism. And they run this through the merit order to decide the market clearing price and to sort the winners for the bidding and offering. And also, we open the demand side competition to relatively larger scale of consumers. So mainly at the beginning is if the consumers, they have the power demand about 1 megawatt, they can enter the market to find the retailers to trade. And moving to the second stage, that's basically after 2000. So we moved the shape of the wholesale market from electricity pool to bilateral trading. That means it's relatively decentralized. We don't need the centralized agent to sort all the bid and offer together. So for the sellers and the buyers, they can directly enter the electricity market to negotiate the price, the volume they want to trade. And at the beginning, it's only limited at England and Wales. It's called NATA. And later, it's expanded to Scotland. So all over the GB, we have this bilateral trading across different regions, different nations. It's called beta. And this shape, this mechanism lasts until present. Still, we have this beta scale for the bilateral energy trading, the wholesale market.
Is this confidential or just publicly available information about it?
It's publicly available. It's kind of history, and we use that in teaching materials, in slides, and also for our national energy system operator, they introduce the history, the evolution of energy industry. I think it's publicly available everywhere.
No, I meant if you want to go and trade bilaterally now, if two of us want to trade, is there a place that I can learn what the price is?
Yes, we have the information. It's publicly available for the information
Online?
of the trading volume, the trading price. But the seller or buyer, the individual information is not.
Okay.
Yeah, because for this bilateral trading, they deliberately protect the information for the individual seller and trader. But for the market price and the volume, we can access all this information.
And when they trade, do they have to observe the grid constraints or not?
Yes, they have to go through the negotiation and reach to the consensus, to decide the bidding or selling price. And all this information, that's also later on, I will put all this information to our agent-based model to simulate the market operation. I think for most of this bilateral trading, it's in the forward market that can up to 7 years before the physical delivery.
Right. So it's really not, it's not online. It's not for tomorrow. It's more like purchase
long term.
agreements,
They provide some certainty and confidence for generation companies, the energy suppliers. And later, move to the third stage. We look more about the climate change, the carbon emissions. So back to 2005, all over the EU, the European Commission, they launched the emission trading scheme. And also later, the UK developed their own emission trading scheme called UK ETS. So the carbon price is relatively higher than the EU because there is imbalance in terms of economic development across Europe. So for Western part, they are relatively high income country, so they need to move faster and quicker for the decarbonization. So for the UK, they introduced, it's called price support. So on top of the carbon price across Europe, they have some price foundation at the bottom to increase the carbon price. So that's a emission trading scheme. And also back to 2010, we introduced the electricity market reform. So mainly for purpose like no matter electricity pool or bilateral trading, that's more about the wholesale market, the dynamic supply-demand balance to match the generation with the energy consumption. But later also the energy system, they realize they also need the capacity, the adequacy for the system with the increase of the demand. And they need to have more power plant, more generation capacity to meet this demand. And also, in the meantime, encourage the renewable investment. So we have the capacity auction that's held almost annually for all the generation company. They can enter this auction to decide their offering price, how much size, which location, which particular technology they will build to increase the power system capacity. And also, we have this contract for difference. That's mainly for renewable-based generation and nuclear, give them relatively fixed price. So if in future the price drop below this pre-agreed price, then they will get compensation from the government. And also this is two-way. If you sell this renewable-based or nuclear-based energy with a price higher than pre-agreed price, then you need to pay back for the government. That gives some certainty and confidence for the renewable investment. And until current, that's a very recent stage. We look more about the flexibility and the whole system integration. So back to 2019, we have the legally binding net zero target with the aim of net zero transition by 2050. And recently also we have the clean power by 2035. That means a majority of generation, the power plants, they should be clean technology, renewable-based generation. And also, they regularly review the energy market design. Is that sensible? Is that still efficient? Can we also still use the market signal to incentivize the low carbon transition? So we have this REMA, the review of electricity market arrangement. Previously, for example, we don't have the locational price, but we have a lot of congestion issue. And we are just in discussion to introduce this nodal price or zonal price. And for the contract side, in particular, for the flexibility from consumers, we call it consumer lead flexibility. How can we pool the resources, the actual flexibility from, in particular, light industrial and commercial consumers together to help balance the supply demand for the power system? And also how we can have a credible pathway for the net zero transition. And this is the summary of all the pathway, I think, from three perspectives. First is more about the market design, market mechanism. So through the initial liberalization back to 1990, and we introduced the competition for the wholesale market, for the demand side, the retail market. And later we turned to bilateral trading, and we introduced the energy market reform to increase the adequacy of the energy market. And from the carbon reduction side, from the EU emission trading scheme, we moved to the UK-based emission trading scheme and the net zero transition. And from technical side, the system operation, so start for electricity pool is relatively centralized, and later we moved that to decentralized supply-demand balance. And also with the bilateral trading, we have the balancing mechanism that's managed by the power system operator. So at 1 hour before the gate closure, they will say if for the overall system, they can balance the supply demand. Or if not, they need to open the market for the balancing mechanism with relatively higher bidding or selling price to help better balance the supply and demand. And for now, we look more about the flexibility and the smart energy system. Yeah, and this is the overall. So I put all the different types that's present in JB electricity market together. So for example, we have the wholesale market, and that's included the forward market that can up to 7 years before the physical delivery or even longer. So the sellers and the buyers, they can sign the contract to decide the volume and the price. Also, they have some kind of risk management portfolios. For example, they can use futures or options to fix the price to give them some certainties. And over the spot market, that's more close to the physical delivery. So that means the uncertainty, the risk need to be well managed. And at the beginning, we have intraday and the day ahead market. That's still through market mechanism, but because it's close to the physical delivery, so the price will be relatively fluctuating. And for the offering price, that's probably relatively higher. And until 1 hour before the gate closure, before the physical delivery, that's gate closure time. So the market operator hand over the management authority to the electricity system operator because they know better on the physical constraints, the supply-demand situation. They can better manage the supply-demand balance. Instead of using market or pricing-based mechanism, it's more about physical. So if they call any generator to increase the power supply or cause any flexible load to change the demand, they need to consider not only for the cost, but also the physical distance, how soon they can turn on or turn off this generation or consumption. And for the retail market, we have energy suppliers. They can sign the contract with consumers. There is no geographical limitation. So the consumer, it's just like mobile service. The consumer can pick up any energy suppliers to sign the contract over the next few months or next few years to fix the price or use them particular offer for the electricity supply. And all the clean technology, the rooftop solar panel, the EV charging infrastructure, also the smart meter, that's all facilitated by the energy suppliers. For example, I think the largest one in the UK is Octopus Energy. Yeah, and also in the meantime, we have the ancillary services. So it's mainly to provide the flexibility to the power system. And they have a two-stage contract. One is standby. So the power system operator will sign the contract with the additional flexibility providers. If you have, for example, if you have this battery capacity, can you stand by whenever we need in the power system? We call you and you release this power to our system. And so the second stage is for the calling contract. They will get additional payment. And also, as I mentioned, we have the capacity auction, capacity market to ensure the adequacy. And also contract for difference is more encourage the renewable and the nuclear-based generation. And this slide summarizes all the key stakeholders all over the JB electricity market. So that's integrate the physical power flow, the capital flow, and also the policy mechanism together. So on top of this slide, that's more about the UK government. We have a particular department. It's called DENSNIS, the Department for Energy Security and Net Zero. That's make the general policy how we can move the energy system for net zero transition. And also we have the regulator, it's called OFGEM, Office of Gas and the Electricity Market. That's more protected for the benefits, the interest for the demand side, the consumers. And also they monitor the companies with the nature of natural monopoly, like the utility company, the transmission or distribution network operators, because all their investment decisions, all their costs or income need to be closely monitored to ensure the fairness across all the market. And also we incorporate the real-time operation that's in half-hour interval with the long-term planning and investment. So at the bottom, we have the NISO that's dynamically match the supply and demand balance and maintain the system within the constraints. And in JB, currently we have 56 generation companies, and in total, they manage about 1,127 power plants all over the JB. And they decide the investment decision, what additional technology capacity they will build at which location. And also we have the energy supplier. So the energy supplier, they purchase the power over the wholesale market from generation company. And later at the retail market, they sell this power to their contracted customers. And also we have the distribution network operator that's manage their geographical boundary within that region for the distribution network, the medium and low voltage distribution network. And also we have the transmission companies that decides the reinforcement or the investment for the transmission networks. And the good thing in the JB electricity market, we have all the data open accessible. no matter for 56 generation company, which location with technology for their power plant, and also for energy suppliers, what's the distribution of their contracted customers, and what's the scheme mechanism they use to contract with their customers, and also for the planning decision, reinforcement decisions for the transmission network operator and the distribution network operator. So that's motivate us to collect all this data over, I think, past almost 10 years and put it in the multi-agent data-driven modeling to model the decision-making and the interaction across different stakeholders, different agents. I think I just temporarily exit this slide and I can show our web-based platform. I stop sharing first. And here, sharing.
Nice photo. This photo.
Yeah.
Yeah.
Right, yeah, sure.
Who's on the infrastructure planning?
It depends on if it's for the transmission network, that's it's in the national grid group, and we have the national grid electricity distribution, the NGET, the NGET, and also national grid transmission, and also the NESO. NESO more about the dynamic real-time supply demand balance. And the asset owner is for the NGET and the NGET, the national grid electricity distribution and transmission. Although they belong to the same group of national grid, but they are independent, completely independent company. They don't interact the decision or communicate with each other. They make completely individual decisions. Yeah. Any other question? Yeah. Sorry, I forgot to mention if there is any question from either online audience or here, feel free to ask or interrupt me. Okay, right. Then this is our web-based platform for the agent-based modeling of the GB electricity market. So on top over here, that's the different agent. So for example, we have the 56 generation company, and to here. And if from this drop-down menu, we can pick up any one of these 56 generation company, and it can visualize the portfolio. So the circle size means the capacity of different generation technology. And the legend over there is the generation technology. And also, we model the capacity auction. So in that way, we can predict from current year until 2050 annually how the generation capacity will increase. So for example, we move here and we can see the capacity increase. It take a bit longer. And also we analyze the capital flow for different generation companies in every year to do the cost benefit analysis, the NPV, the return on investment, so they can better decide which location, how much capacity, which technology they will build across the JB energy system. And also that's interact with the input as policy decision, the market situation, so they can make better decision. In the meantime, increase their own profits, but also move the energy system towards a net zero transition. And also, this is the energy supplier. We collect all the information from the energy supplier over the JB, so we can analyze the distribution, geographical distribution of their customers. And this is the network operator. So we can run the contingency analysis in every half hour from current year until 2050 to identify the critical line and what's the impact for the new connection of distributed generation or the demand load, for example, the large-scale data center, how that will impact the power system, the constraints. And also, we run any half-hour carbon emission flow and the power flow because there is improportional distribution for the power flow and the carbon emission flow. So for example, for Northeast or the Scotland part, they generate power most from clean energy, like the wind, the solar, and also they send the power to the southern part, like Birmingham. And from the right-hand side, you can see it's the intensity, the carbon intensity is relatively lower because that's clean energy. So with that information, we can better quantify the responsibility for the carbon reduction in different regions, different areas. And also, we evaluate the capacity headroom, the capacity margin in different locations. That's information also helpful for connection of new distributed generation or new load. So that's the installed capacity minus the peak demand. We can know in which particular area we have extra generation that can connect with the new load, no matter the industry or commercial consumers.
The grid data is not publicly known.
For now, it's all publicly available for most of data, like the generation, the power plant.
No, I mean power grid.
It's not. It's relatively
So how do you
sensitive.
get that?
The NISO, they have two models. One is simplified JV power system model. They have the information, and also they have the full node. It's about 1,000 node for JV power grid. And I think most of data, like the resistance, reactance, the cable, and the location of the node, they have that data available. But for some like operational data, the operational log, they don't have that publicly available. So we can use this publicly available data to build up the like power flow analysis and the contingency analysis to analyze these features, the parameters for different cables, different nodes.
So for the pool, the supplier itself doesn't interact, or they were put as an agent, but it's just the data is diverse. Before you track all of this.
Yeah, so for the trading behaviors, we have the finally decided market clearing price, but the trading behavior, we don't have that information. So we have to simulate the individual decisions for the energy trading, like what's the bidding or selling price, how much volume they want to trade. And we use the finally market linear price for all the different energy suppliers to collaborate our simulate output, the result.
So all this are treated as an individual agent.
Yes, for example, for the individual generation company, we treat that as individual agent because they only maximize their own profits. It's similar for the energy suppliers. So we calculate the cost benefit, how much the income they earn from their customers, and how much cost they buy from the wholesale market. And each individual energy supplier, they also maximize their own profit. And in the meantime, they manage the risk portfolio, how they can better use filters and options to mitigate the risk.
Is there someone on the other side of those trades? Like, who are they making the futures and options with? Are they with one another or with kind of a finance?
Yeah, it's mainly through the exchange. Like I think the stock market in New York and in France, they have the power trading. The market is a platform open to all the individual sellers and the buyers. And also they can, it's more like the insurance. So they can purchase the options of the futures to fix the price. Yeah.
And then making those deals, the agents are making those deals with like
the agent, the third party, kind of third party. So that means the insurance, we take the example of the insurance company. That means the third party, they will fix the price. And in the future, for the real-time operation, if the price going higher or lower, then because they have this insurance, the futures or options, the price get fixed. They will get the payments for the difference for no matter the increase or decrease.
So I want to conduct a generation expansion model for, I see you have generation capacity for future years. So you get this data by solving a generation expansion model.
It's actually, we model the planning, the capacity auction mechanism. So that means each individual generation company, they look at their own generation portfolio, different technology, the capacity, because most of the generation company, they expand based on their existing portfolio of technology that's easier and sensible for them make decision. And also they look at different location, because different location, they have different connection charge from NISO. That's also relevant to the capacity margin in that area. And they consider this different input information. And we use multi-agent reinforcement learning to adapt their decision-making annually, how they can participate in capacity auction. So they can decide, for example, for the next year of capacity auction, they can decide if they want to expand the wind farm, the wind generation, how much capacity, in which location, and how much that would cost. And once they decided for individual generation company, they submit to the capacity auction. And we have the stack model to clearing to decide the winner for the capacity auction. And also we consider the field year, like 10 years, 20 years later, they can commit to run for this generation power plant. That's the way we model the annually investment and planning until 2050.
So you get this capacity by the reinforcement learning method instead of the optimization model.
At beginning, it's optimization. So because for the generation company, they need to maximize their profit, and later to accelerate the computation process, because in every half-hour interval and from now on to 2050, that's a very large computational power. So we train the reinforcement learning model. The policy of the reinforcement learning is actually the objective function. So they use the objective function, the profit, how much profit, to measure how good the decision would be, and give them feedback so they can adapt the real-time situation, like the market clearing price, how much additional capacity the government announced. That's the external information, the state information from the reinforcement learning perspective. They collect all this information to make best decision at that particular time. Yeah. I think then I can move back to my slide. That's the second part of the work I would like to introduce. It's about the whole system integration. So we integrate multiple energy vectors, electricity, heating, cooling, hydrogen, and across different sectors, the built environment, the transport, the healthcare, and the industrial sectors. We want to maximize the flexibility across different sectors and the vectors, and also find the synergy across this multi-vector cross-sector integration. And this is a bit background information. Why we call it whole system approach. That means we integrate everything together. Why we need that? So first, we have increasing instance of the extreme weather event, like the Iberian Peninsula blackout. And also in UK, we have wildfire, and that's the secondary substation of Heathrow Airport. And that's result in the flight delayed for more than, I think, 1 day. And also in the meantime, we have increasing instance of cyber attacks. And all this extreme weather, the natural event and the cyber attacks, they add together, they have the cascading impact to the power system. Like the Iberian blackout. At the beginning, it's just because of the acceleration of the solar panel. And later, they trigger the protection system of the power system, and result in the blackout across the Spain, Portugal, and the southern France. And also, because all the different networks, they have interdependency, like the electricity network, the gas pipeline, the transport system, the communication system, and service system, they all rely on each other. And that's also increased the secondary impact if we have any of this in one. So that's motivate us to integrate different vectors all together. So I think the vertical dimension is for different energy vectors, the electricity, heating, cooling, hydrogen. And the horizontal vector is for different sectors, how we use this integrated multi-vector system to solve the issue, solve the problem in these particular sectors. For example, we have the electrification of the heat. We use the heat pump to provide the clean thermal demand. Also, we have the electrification of the transport system. And also the hydrogen, they can provide multi-vector flexibility. So, for example, if for some area they have extra renewable-based generation, they have used the extra renewable generation like the wind in Scotland. They can use that for the hydrogen electrolyzer to produce hydrogen locally. And whenever there is peak electricity demand, they can use the hydrogen fuel cell to convert hydrogen to electricity to meet the local demand. And also traditional technology like CCHP that can also improve the efficiency. And the transport is not limited to the electric vehicle, but also like the airport, the maritime system. And this is how we can better maximize the flexibility across different spatial and temporal scale. We have supply-side flexibility resources, demand-side flexibility resources, and in the short term and the long term, like the long duration energy storage that can provide the long-term flexibility and across different energy vectors. And this is one of our recent projects. It's funded by Horizon Europe. I think the good thing is since last year, the Horizon Europe also opened application for US and globally. So all the country, they can apply for the Horizon Europe to solve the global issue, global challenges. And for this project, we want to look at the hydrogen integration for the demand side, for the community level. And we want to tailor our solution to the particular resources and conditions in that particular area. So for example, if we can blend hydrogen with a gas pipeline, we can send that through the hydrogen boilers or even hydrogen refueling station. And if we have vast resources of renewable generation, we can use the electrolyzer to produce green hydrogen. And we evaluate the most suitable hydrogen integration pathway for a particular area. And for this one, we work together with other countries from both academia and the industry across Europe and also globally. Like we have University of Sydney, the National University of Singapore, and Sri Lanka, as well as the University of Auckland in New Zealand. We want to find the most suitable hydrogen integration solution in this particular area. And also we have a quite interdisciplinary team. So our University of Birmingham, we are the coordinator for this project. And we have experts from social science, economic background. So not only look at the technical side, we also see how we can align the market arrangement to accommodate this hydrogen integration to facilitate the future increased proportion of hydrogen production, and how we can better inform policymakers to make best decision to move the energy system to clean energy transition. Also, we consider the factors like the seasonal political issues and how that impact the cost uncertainty or risk for the future clean energy transition. Yeah. And
So can I ask a question?
Yeah, sure.
So if if you find in your research that, it's good to combine gas and hydrogen, let's say, where do you go? Who listens to you? Where do you give that information of data from your research and who takes action?
In the UK system, the UK government and the regulator, from time to time, they
So they
open,
issue new regulation? What is the
they open
tangible
the
thing
policy consultation.
to do
So
what in
to
this particular case?
collect the evidence, and they will review the evidence and say if their policy making aligns with this evidence or if they make anything wrong. So for example, for this hydrogen, so the upstream, they open the policy consultation for regional energy strategic plan. And they collect evidence from industry, from academia, and from our research result of the practical implementation. Is this a good way for this particular region to integrate renewable-based generation or the hydrogen? And if there is anything wrong, because we formally submit this policy evidence to the UK Parliament or to the upstream, and they will review it. They will get back to us. And
Just to come to the heart of the question, I think that regulators usually don't understand these very nitty-gritty technical issues.
yeah,
So
that's
how do you deal with that?
that's a major barrier. So in our practice, we call it human in the loop approach.
Mhm.
So for example, that's why it motivates us to design the web-based visualized platform, because in particular for the research, they can't really easily understand the complex algorithm or the context behind the decision making. So we try to visualize directly linked to their
And then
objectives.
you can show them the
Yeah.
data you want to show them and what you want to get out. So you can be biased. Who is at the end, in a sort of very objective way, deciding that this is actually.
It's,
I think we really have a problem with that.
yeah, I think it's, yeah.
Because it sounds too good to be true, right?
Yes.
We do our study
It's quite
and-
ideal. Yeah, in
Yes.
particular from academia, we always say this is optimal decision.
Yeah,
But in practice, they have a lot of like real world constraints. We can't get that practical point. So we use this iterative manner. So we have the stakeholder engagement workshop to find the representatives in different stakeholder groups to collect their feedback, their real-world decision-making, to calibrate our model. And we convert for example, we have the semi-structured questionnaire to collect what's the feedback, what's the real decision instead of the optimal decision from model, and what's the discrepancy. And also we use natural language processing, not based by ourselves, but by the AI to process this questionnaire and convert this descriptive text into quantitative input and use that to further calibrate our model. So in that way, we can realize the physical real-world constraints from different stakeholders. And another task, it's from SIGRI, the task force we engage. We form a task force, a panel, and we want to identify the representative stakeholder group and the leading industry, and also the SME. It's quite diverse, quite equal. And we want to collect the feedback to do the interview, to collect the information. What's the barrier we didn't realize in our model, and how we can better align our theoretical model to their real-world practice.
So are there some success stories?
Yes, I think it went through quite smoothly, and we just finished at the beginning this year. We just finished the first phase of the SIGRI project, and we engaged, I think, more than 100 industrial stakeholder group representatives. We use either the interview, the online questionnaire, or the stakeholder workshops to collect that. And we convert all the feedback from these representative stakeholders, put back to our model. And also, in the meantime, we use explainable artificial intelligence to better visualize, explain the motivations, the reason behind our optimizations, and to better let the stakeholder know why you make that decision, why you note, and if you change a bit for your decision, what you can improve for your own benefit and for the system interest. Okay, thanks. Any other question? Right. Yeah, and this is also our trial for the renewable. So use renewable for the hydrogen electrolyzer, and we store the hydrogen, and also we have the thermal storage to store the thermal power of hydrogen fuel cell. And also the second part is integrate the electricity system, the multi-vector energy system with maritime, because for now, maritime is the national priority of the UK, the maritime decarbonisation. And there are lots of uncertainties for the operation, for example, the vessel, because they need to decide the optimal route, speed, arriving time. But also in the meantime, because for most of the ports, they move to the clean energy generation, the clean technology. But that also depends on availability of that clean energy production. So we align all these uncertainty factors, like the weather conditions, the sea state, sea environment, and the voyage planning, all the way to the availability of the port resources to reduce the waiting time, to optimize. It's similar like the multi-stakeholder optimization model to fund the optimal decision for the vessel operators, for the port operators, also for the policymakers. And also we integrate multiple vectors together because the majority electricity consumption for or energy consumption for the vessel is the propulsion power to drive the vessel. And we want to fund the flexibility to improve the energy efficiency for the maritime operation. So that's delivered from our two national centers in Birmingham University. So we have Birmingham Energy Innovation Center, for which we have the hydrogen refueling station. That's not only for maritime, but also for all the bus, hydrogen bus all over the Birmingham. And also we have the railway center with the capability of transport digitalization. We work together along with Nordic partners, the Aalto University in Finland, the Port of Helsinki, and also the Weiqi line. And also this is our integration for the building block and the built environment. That comes from another Horizon Europe project. So in that one, we develop our federated digital twin, the 3-layer digital twin, to fund the synergy, to optimize the core benefits for the indoor system, the operation of indoor energy system, like home energy management system, and also the building materials, because different materials, they have different conductancy and transmittancy, how they can improve the energy efficiency, and also across the community level, how we can integrate different types of customers, different load patterns to fund the flexibility, to facilitate the community energy sharing. In that sense, we can put all the resources together to keep the capital inside the community. And we found 4 demonstrators across our partners. For example, in the UK, we have a lot of historical heritage, and they don't allow us to install clean solution like the solar panel or EV charging. So how our digital solution can be context sensitive to align with this constraint. And also in Vasa at Finland, it's not part of Finland. They have data center, and they recover the waste heat from data center to supply the thermal demand of the office space. Also in Zagreb at Croatia, they have two buildings pending for retrofitting, and one is fully monitored with smart meters and sensors. The other is not, and that's good for research. So we have the benchmark and see how our intervention can improve the energy efficiency. And also for the Polish case, it's kind of new build combined industrial and residential site, how we can integrate clean energy solution for that. Yeah. And the third part is how we use data-driven digitalization to support the planning and operation of the energy system, in particular for the demand side. Yeah, I will be quicker. Yeah. So first, we realize the digitalization digital twin is kind of magic hammer, but we can't take every component of our system as a nail. So we need to identify which place is best for use digital solution and how we should better use this digital solution. So this is the typical voltage level across the JB power system. So for high voltage transmission and medium voltage distribution, this historically have been intensively monitored, like use SCADA system to maintain the constraints to monitor the power flow, the dynamics of this system. But for the demand side, because historically the load pattern, they are quite certain. For example, the residential typically they have 2 peaks, the midday peak, the evening peak. And for the industrial, it depends on nature of the industry. They are quite predictable, quite certain. But the thing is, for now, we have more and more integration of clean technology, the electric vehicle, the solar panel, and different load, different demand. That's caused a lot of uncertainties. But still, the issue is we don't have that incentive monitor system, the smart meter, to roll out everywhere, every customers. So we realize that's the best way, best place. We use digitalization to assist this monitoring, operation, and scheduling. And also that can avoid the cost for investing the smart meters and the sensors. Yeah. And also we identify the main requirement from the power system operator, in particular for distribution network operator, what's the need and how the digitalization can fulfill individual requirements, including like the long-term planning, real-time operation, the market trading, and the asset management, both physical asset and the non-physical asset, and also grid connection. And the digitalization can solve this issue from different perspectives. And this is our core research methodologies. So for some like rural area or semi-rural area, the topology or parameters for distribution network is not monitored, it's not visible. So what we do is we work with the distribution network operator and to train their monitor data and map that with generative AI to unmonitored area to generate the topology and the parameters for their distribution networks. And also we use the statistic approach to predict the scenarios, the uncertainties for future transition, including both like the high impact, low probability scenarios, like extreme weather event, or the like low impact but high frequency scenarios, like the energy imbalance. And we use this whole system integration to co-optimize across different vectors. And that's our solution. We use explainable AI visualized platform to better communicate with different stakeholder groups. And we collect their feedback to feed in our model to collaborate our optimization making. And this is a project previously we worked together with the distribution network operator in JB. So we built up the digital twin for their secondary substation. So on top of the slide is a physical distribution network. And at the bottom is our digital twin model. So similar like the nationwide energy system modeling, we combine the long-term planning with the real-time operation. So long-term planning, we look at the network configuration or reconfiguration and the change of load pattern of the connection of new customers, and also the future grid technology integration. And also we run the real-time like power flow contingency analysis to evaluate if the system can still hold this increased technology connection or the load connection, and we send the best decision making back to the control room of DNO. And also to better help, as I mentioned earlier, the context sensitive planning. From the Google map, we can generate this 3D model to visualize the different composition of customer group, what load pattern looks like, what's available space to integrate this clean energy technology. And for example, if they close to river, is there any potential for future risk for like flood or any heat wave extreme weather event? And this is our stochastic approach to analyze the potential impact of these uncertainties of their local energy system. And also we run the clustering for the typical load pattern for electricity and heating, and map that typical load pattern to the socioeconomic and the demographic features for the individual consumer group. So to protect their privacy, we map it at the postcode level. That's basically across one street, what's the average load pattern looks like, and what potential intervention we can develop to improve the energy efficiency. That also comes from our previous project from UK government to help the Oxford County Council for the clean air source heat pump integration. So we can identify what's the main barrier for individual residential consumers. They replace the heat pump, the gas boiler with their clean air source heat pump. And also this is our expand of artificial intelligence. So we collect all the data like the localized generation, the demand, and also carbon behaviors for the individual consumers from their smart meter. And we process this data along with the price signal, the time of use price. And we calculate the price elasticity across any 2 time interval over a day. So that means we have half-hour interval. So we have the 48 by 48 matrix to visualize their elasticity. So that means we have the information how they will respond by changing their behavior to the price signal. And for this color, the visualization, so the brighter color means the higher elasticity. That means if we change the price signal, we can impact their behaviors at that particular time horizon. And for the darker area, that means the lower elasticity. That means the load is unchangeable or the generation is not changeable. And we map that, we call it the internal features of individual consumers to the potential energy behaviors, the local generation, consumption, storage, and like EV charging, discharging behaviors. And also we train a large language model to directly generate, to read this metrics from their smart meter and to generate a prompt to explain what their energy pattern would be. So this directly generated by the large language model, directly read from this metrics from their smart meter. It's purely automatic system without human intervention. So they can better aware of their features and they can know what's the better intervention they should make. And the last bit is from market side, the community energy sharing. Also,
Can you summarize this part?
yeah, sure. Yeah. It would be super quick. So also, it's mainly 2 aspects. First aspect is we integrate the electricity trading with the carbon credits. So for the demand side, if they integrate like the solar panel, the heat pump, clean solution, how we can credit these customers. So we combine this together. So in the meantime, we track the energy flow, the power flow of consumers. We can also track the carbon behaviors and the potential carbon reduction. And we give them the corresponding compensation for these low carbon behaviors. This is the integration for the individual household, the electricity system and the thermal system. So we want to use thermal system with like air source heat pump and the thermal storage, like the hot water cylinder, to increase the flexibility for the electricity consumption and the electricity sharing. And also we develop the market mechanism, and that's also from our previous project. We work with DNO. We pick up one street to do the trial for the community energy sharing, and we develop a mobile-based software to allow the individual household, if they have extra localized generation, they can send this extra generation to their neighborhood with both lower price, so they can remain the capital inside the community. Yeah, so that's finally key takeaway. So 3 aspects. First, if we want to move the system to net zero, the digitalization, digital twin, they can achieve the net zero transition with least cost. And secondly, we need to unlock the flexibility and the visibility from the last mile. We call it last mile of power system. That means the demand side. That's more and more important in future energy system. And also from market side, the local energy markets, the community energy sharing scheme that can empower the community for the future low carbon investment. Yeah, that's everything. Thank you very much. We're running up out of time. Yeah, if there is any more question, I can.